Good morning, good afternoon. Welcome to today's webinar. I will kick things off with Greg in a couple of minutes. We'll give the last few people the chance to filter in after their previous meetings, and then we'll get started. Hi everybody, welcome to the webinar. With me today is Master Geomagician Greg George. He's going to be spending some time talking you through how reverse engineering and inspection technologies can help you improve manufacturing efficiencies in turbine blade production. He's going to walk through a bit of background, then how averaging your mesh can optimize part accuracy, how to transfer entire feature trees into your favorite external CAD package from the Geomagic software, how automating your workflows with visual scripting can enable huge time savings, how to gather custom profile measurements such as twist analysis quickly and easily, and finally how working within one base scan system can help raise invaluable business benefits. Over to you, Gigi.
All right, thanks a lot, Guy. Yeah, so I will be the main presenter today, and I'm excited to talk about the turbine blade industry and how our products apply to that field. But real quick, I always like to show this slide to make sure everybody knows that if you have any questions along the way, you can put those in the Q&A. And if we have time at the end, I'll try to answer a few of them. And then of course, I can always follow up later and answer questions directly. And the session is being recorded, so we'll send that out afterwards. So if you have any other questions, feel free to use the Q&A. So with that, I'll just go ahead and get started. I think a lot of this information on this first slide is probably known to a lot of people, but just to reiterate for people that may be newer to this industry, I'd like to talk a little bit about turbine blades. You know, they're an individual component that makes up the turbine section, like whether it's a gas or a steam turbine to generate power. Blades are responsible for extracting energy from the high temperature pressure gas produced in the combustion. But the reason why this is important is these devices kind of push the limits of what is possible with manufacturing, right? In order for these things to survive in a difficult environment and produced from exotic materials and alloys and the cooling and heat, the pressure that we put them under, fatigue is a major source of failure for these gas and steam turbines. So these are a great example to show like very complicated, high tolerance geometry and kind of the limits of what manufacturing is capable of in the world today. So today we're focusing on the turbine blade industry, and the problem is, as you can tell, we're pushing the limits of what's possible with manufacturing, but these turbine blades in this manufacturing environment face the same high temperatures and stresses that we talked about, and even high vibration, which causes failures and time to wear out. So all three of these factors lead to the need for replacement. And as you can see in the assembly pictures that I have up here, there's a lot of them, right? So this first bullet point is, we're putting them under a lot of stress from centrifugal force, with lots of force on those blades. And then additionally, they're at extremely high temperatures, which can weaken the blades and make them susceptible for creep and failures. And then of course the vibration is extremely high RPMs. And again, these are just kind of like the limits of what happens in this manufacturing environment. So these are some of the specific challenges, right? So in general, we have the power gen blade world that is kind of an aging infrastructure. Actually, believe it or not, like these facilities actually outlast a lot of the projections, right? So they're overbuilt, and they've lasted for decades longer, and their lifespan is extended. Now, the reason why I bring that up is if the lifespan of these facilities with this power gen is exceeding expectations and we're actually using them longer, it means that some of these designs are very old. So you need to basically source replacement parts, right? So often the market and regulation controls constrain the supply chain, as all of us have seen throughout the world. And then that changes how you can source replacement parts, right? And of course, these are very complicated pieces of geometry that we're using, and it's very expensive to manufacture. And then they're also held to extremely high tolerances, right? Every micron could mean millions of dollars to the bottom line with efficiencies, which is the last one here. Every micron means millions of dollars, so very high efficiencies. As you can see, here's a very worn out blade. This is an example of why you would want to recreate these objects in order to replace them. So where do we start? The starting point for recreating these objects is starting by capturing the geometry. And there are a whole host of partners that we work with that make different types of scanning equipment to accommodate a variety of needs depending on the size and shape and alloy of your blade, right? Today, we're just going to focus on the general specifics and benefits of these types of digitization. So like I just grab a few screenshots along the way of different scanning devices, digitizing devices that have been used in this industry over the years. But the reason why we talk about scanning is scanners are almost made for this type of application, right? They easily capture very complicated geometry, which I think blades fit right in that category. They're very fast. Scanners are very fast at capturing extremely complicated geometry, especially the ones these days that are coming out. They're amazing at how much information, how much detail we can capture at the rate that we capture it. Scanners are mobile, so sometimes that comes into play here, but it is a benefit that I like to bring up. Depending on the scanner you get, sometimes that is a part of the workflow where you might want it to be mobile. And they can capture a more complete picture of the part rather than traditional measuring techniques, as you see below, without my showing a pair of calipers and even hands there, but like, they're extremely accurate and they give you a high definition picture of the shape of the part. And they can function also as an archive. This is one that many people forget or overlook. But if you capture the shape of this part, it's almost like a snapshot in time that you can always reference going forward. So even if that blade was to, for some reason, get destroyed, you have that digitally captured as an archive. And then another one, which we'll talk about here, another benefit of scanning, is if you scan these parts, you actually have the ability to take multiple parts, multiple examples or specimens of the same exact piece and average them together in order to more effectively reverse engineer the shape of the part and recreate a new one, right? And then another one that sometimes comes into play is scanning is non-contact, so you don't have to destroy the part when you scan it, and you don't have to touch it or deflect it in any way. It's just a visual line of sight for most of the scanners. So that is the benefit. You have to start with some sort of digitizer or scanner to capture the shapes of these pieces. And then that's where my workflow will pick up here with our software suite. So you have all these devices that I referenced earlier on that slide, many different devices out in the market that capture the shapes of these objects. And then we need to get that information over to some sort of manufacturing. In this case, primarily is going to be CNC, but I just point out that you send it over to CAD, which may then jump from CAD to CNC, which is a very common workflow. But then some people in the future, obviously, additive is an option as well to be able to send things over. But these devices historically have captured this type of information pretty well. But there's always been kind of this missing piece in the middle of how do I get that information from these types of scanners over to the different CAD packages or CNC packages. And that's where the first product that I want to talk about today comes into play, our DesignX package. So our DesignX package specializes in sitting in between the scanners and the CAD and CNC manufacturing world to create the proper geometry to go into those workflows. So essentially, the way the workflow works is on the left-hand side, you have the type of data that comes from these different scanners. Depending on the specific one you choose, you may have two different kinds of information coming out of that scanner. One of them is a polygon object, which is this one on the left-hand side, which is a bunch of triangles that are all connected together in a high resolution. And I give this little magnifying glass to kind of show. It's a little bit difficult to see through the meeting, but those are a bunch of triangles connecting together to form that surface. And then another form of information that you get from these 3D scanning devices is a point cloud, which is a very similar type of data set. Triangles are just a little smarter because we take those measurements and connect them together into triangles, where a polygon is a point cloud is just a bunch of 3D measurements in space. And sometimes they have information as to the direction and color of each dimension. But the problem is this type of information does not fit well in the CAD environment. So that's where DesignX is going to take this type of information, these scans from point clouds and polygons, and get them over to CAD. So one advantage that I discussed earlier with the turbine blade industry specifically, and this works for others as well, but this has been very handy over the years. And this is the reason why we designed this tool specifically originally a few years ago, is, you know, if I take one blade and I reverse engineer it, how do I know that that isn't like the worst example of that blade off the assembly line? Or if it is extremely worn, how do I design that wear out of that shape and create a great starting point that is where the original design was supposed to be, right? And one way that we can accommodate for that is we can take a bunch of scans. So you could scan a sampling or a lot of these scans and then take them and overlay them on top of each other and average them together, and then take that averaged part and reverse engineer off of it. So you have a better way to cover yourself in averaging out some of those tolerances and errors in the defects in the shape of the part, and thus getting you closer to that original design intent to then make these parts anew, right? So, this is a major advantage of 3D scanning, is that ability to average many, many parts together. And I'll show a brief example of that in the live demonstration portion of this presentation. So the other thing that I hinted at that I can explain a little bit more about now is, like we talked about with that blade, is many times the part that you scan isn't actually what you want to manufacture, right? It has a lot of error in it, whether it comes from tolerances of the original manufactured piece, or wear, or it's defective. You need to have the ability to design a part with the original design intent. So you can reverse engineer a part and then make it what we call as built. So I use these extreme examples on the screen just to demonstrate extreme examples of what that would look like. Is I scan a person's hand and I make exactly that shape as closely as I can within tolerances of the scanner and the manufacturing devices. But with the turbine blade industry, what we really want is to scan that part and then override those dimensions to be what they should have been, right? And again, it doesn't matter where that error originally is coming from. We're trying to design back in that original intent. And then there are examples in the industry of doing both, where you fit something exactly as is and then you add design intent later. But that really doesn't necessarily apply to this application. I just leave that in there just to show that that is a possibility. So now what I want to do is I'm going to open up our DesignX software. And you can see that I have a blade here on screen. I'm going to go ahead and hide that one and show how an example of, here are a bunch of blades. I went ahead and scanned 10 different blade examples here, and I have them overlaid on top of each other. And you see that if I just show only this one, you'll see there's that one. And then you can turn all of these on and off. So I have 10 different examples here. And some of them have a little bit of error in them and some of them don't, right? But we have this functionality inside of our software that we built many years ago, where I can actually take scans and come over to this average meshes tool. And sometimes this is a really good example for me to use our help file to just show what this software is doing. So I hit the help just so you can see, and it gives you a very good example of what we're going to be doing here. But what I can do is I can actually grab a sampling of all these blades and select them all. And you can tell it that I want to set this for the minimum deviation between all of these blades, and you can set what your maximum deviation is and tell it whether you want to do a weighted average. And then at the bottom, this is a very interesting one here. You can even align pattern targets. And that's part of the reason why I opened the help file, is we actually can average out parts about an axis or about a pattern, a linear pattern in different directions. So in here with the aligned pattern, if the parts aren't aligned to each other, you can actually dictate an axis center, and tell it, I have 10 different blades at these increments, and it'll actually automatically align them together and average them and output the final mesh, where you can select what type of deliverable that you want. So with this, it takes it a second to run. So what I'm going to do for today is I'll go ahead and, instead of hitting the OK, I'm just going to hit cancel out of that. And I went ahead and ran this because it takes a good 2 or 3 minutes for it to run. So I wanted to make sure that I didn't waste everyone's time watching water boil. So in this case, what I did is I ran it and I averaged out this part from that. This is the deliver. You see has averaged mesh as it comes out of it. So this is what it would look like after I get that out. I've averaged all of the meshes together to create one, but we still have the problem here of how do I extract geometry from this in order to model it and send it over to CAD, right? So we have a lot of functionality in the software just to, for example, if you do have anything that you would still want to fix on the mesh, you know, we do have, if you come over to the polygons tab, the ability to come in and smooth information. So if I come over to Smart Brush here, I can actually smooth or relax the shape of pieces. I can fill holes. So you see that there was a defect in the surface of that part. If I wanted to relax that, we've done this stuff for many, many years where we can edit scans, and we almost have like Photoshop type tools to be able to edit scans and fix defects, sample, decimate the amount of triangles, trim, split meshes. All of these are polygon tools, right? All of these things can help me take that average mesh and get it ready for reverse engineering. So once I make any changes to the mesh that I might want to, I can come over and I can start modeling off of this mesh. And one of the most critical pieces of functionality to understand when modeling off of the mesh is one of the most popular tools in here to start with is the mesh sketch tool. So if I come over here and I say I want to create a mesh sketch, I can actually create planes, and let's just create a cross-section plane through this polygon and create a mesh sketch through it. So you see here, if I select that plane, I can intersect that plane through the polygon. We have a ton of other functionality in here. We can create silhouettes. We can cut multiple sections. There's lots of functionality built right in here. We can even account for draft and things like that. But for this specific application, I'm just going to create that one section and hit OK. So just think of DesignX is essentially having all of these scan tools and CAD tools all in one space. So I can cut a cross section through that polygon mesh, and now I have that blade cross section that I can actually just use regular sketching tools. So you see here, I don't want to fit a line to this, obviously, it's not a straight line, but this just shows that I can select geometry and best fit using my sketching tools to the data that's there, right? So I'm just going to go ahead and deselect that and get out of that. But I wanted to just show that it also works with every one of these other tools in here. So if I wanted to go ahead and fit a circle here, I can window in and select where I want that circle to be fit, and I can just accept it. Now, if I want to come back and add dimensions to it, I can. I can come over and say smart dimension, and then add a dimension. Maybe this needs to be 0.552. So I just fit that circle there. And the same thing goes over here. If I wanted to come over here and just window in and fit a circle to that information and accept it. Now for this arc side, you can come in and there's a bunch of different ways. I can use that same selection and I can fit splines to that information just by windowing in if I want to. That's one way. Or I can come in and I can manually draw the spline how I want it to be. So I can click on that circle and I can actually come in and snap to it this way as well. Right, so there's a bunch of different ways that you can go about creating these. Now, I know that from speaking with people in the turbine blade industry, there are very specific ways that people often use to do these designs. So, for the sake of a demo, I'm just showing a few different methods and highlighting some important tools that are involved in creating this geometry. But one way to do this would be to go ahead and create my end conditions by drawing my circles and then coming back here and drawing manually and coming in here and creating that cross section, right? And then from there, you can come back and use our regular trimming tools. You can say, I want to go ahead and power trim this and that there. I want to trim this. And then you can add functionality here. If I wanted to come in, and we'll just undo that last one. Let's do this first. If I select that spline and come in and add constraints and make that tangent, and then before I make that tangent, I'll go ahead and select that circle and make it fixed, and then go ahead and select this and then make that tangent. There we go. So now, and then I can refit stuff, right? So I can drag and manipulate the geometry. After adding dimensions and constraints and relations, I can actually manipulate the geometry and work with it to get exactly what I want. So if I added tangency, it moves the geometry a little bit. I can actually re-snap that and then come back here and do my trimmings and stuff. So you can see I was able to create that. Now, it's not exactly the way we would manufacture this or make it, but that is an example of some of the tools and how they work inside of this tool. Another thing you can even do is if I wanted to just make this one spline all together, I can come in and I can say, I want to fit a spline to this. Here's the tolerance. Here's how many points to use. And then I can create that and look at it, just auto drew that shape itself. Again, there's different ideologies as to like how that you would draw these cross sections. But this is just an example of how you would go about doing it in using some of our tools. Now, just for the sake of time, what I'm going to do is I'm going to go ahead and I'm going to cut another section. And I'm just going to do that same method because it only takes me a minute to do this. And again, this isn't the way I would normally model this, but it is a great example to show how fast it is to cut this section and create all these shapes. So you can see I went ahead and fit all of those with the same amount of nodes to each one. You'll notice that. So we went ahead and I fit all those sections. Now, if I wanted to create a loft between these, I'm just going to loft them all as one. And I can say, let's go ahead and loft these profiles together. And this actually highlights in our lofting tool a new piece of functionality that we've added in this latest version of Design X that released not even a few months ago, right? So we've always had this piece of functionality where we can grab these connectors and align these connectors together. But sometimes you have a very complicated piece of geometry that you may need more connectors than just one. And in the past, what you would have to do is go ahead and manually add guide curves before you come into this tool and use those guide curves as a reference to add connectors, right? But now we added this ability to add connectors here. So if I just click and create extra connectors, and then I can drag them and manipulate them. So you can add a bunch of them here. So I just added one there. You'll see here. So you can create much better geometry to start out with, right? By adding these connectors and aligning them in this way. Now you still have the ability to use the guide curves if you want to. These just help you save time. They serve as a middle ground. It's not as difficult. It's a little faster to add these connectors than it is to add guide curves manually because you have to create another sketch between the different planes and create this. But this helps you create more clean lofted geometry. So you see there that now we created this solid loft between those sections. So that's one piece of functionality, is that ability to loft using those cross sections. We also have the ability to create a loft using a surface loft. So if I just go ahead and turn this off and I come over, I can actually select a bunch of geometry here on the surface of that part. I can come in and I can create a region out of it. So I just selected that geometry and I created a selectable region. Now I can come over and I can create a surface loft, just like this screenshot shows. And I can use that region as a example here where I can drag out. This is like a preview bounding box that goes around the surface, and you are telling it how many cross sections you want and what direction to create that surface loft. So the way I like to think about this is it's like taking a piece of fabric or a blanket and laying it down on the surface for me. And these are kind of like the extents or the size of that surface blanket that's getting laid on top of the geometry there. And then here are the sections. And then when I hit next, our software will go through and automatically create those cross sections. And you can tell it how accurate you want these to be. So if I just say I want these to be 80 points across those surface, or I could even lower it. Let's go down to 50. You'll see that it's a lower resolution surface as it fits through that geometry. Another thing that you can do here is while you're still in the tool, you can turn on the deviation, and I can actually hold control and add more sections. So if there's an area of this mesh that needs more accuracy or more sections to describe that shape, I can do that. And you can even go backwards and forwards through this and add more smoothing or less smoothing to the calculation to create a surface. And then once you're happy with it, you can go ahead and hit OK. And you'll see it creates a surface through all of that geometry. So that's just another tool. Again, this doesn't necessarily mean that is how I will create the geometry for this part. Again, there are very specific ways that people model these parts in the industry, but I'm also showing benefits, other benefits of the software, that help out along the way. So that loft wizard is really neat to be able to create that type of geometry. Now, another way that you can go about creating extremely complicated geometry is to come in and you can actually 3D mesh sketch directly on the scan. So I can come in and come into a 3D sketch, and you can see here that I can draw curves directly on the mesh. As I rotate around, you can see that I'm drawing right on that scan. And this is a way of modeling as well, where you could draw out all of your sections. I'm just trying to do it fast so everyone can see this without spending tons of time watching me click around. But you'll see that I drew all those curves from the network on that surface. And now I can fit surfaces to that as well. I can come over and say I want to do a boundary fit surface, fit exactly to this data, and it fits exactly to the scan data as well. So if I turn on and off the mesh, you can see there's my surface. It's fit through all that information. If I do another 3D comparison like we did before, where I check the deviation, you'll notice that it's going to be completely green because it fits like exactly to that data. It's less than, that's 0.0007 millimeters there. So really, really small deviation between the two. So that's just another way of selecting and creating geometry from the scan data. So you can cut cross sections, and you can create extrudes, lofts, sweeps, fit surfaces with methods like this with the boundary fit surface. And let's say that you modeled this entire thing. Once you do that, you have a history tree over here that you can send this over to CAD. So I'm going to go ahead and say I want to live transfer this over to SolidWorks, just the stuff that I've modeled so far. And I'm going to go ahead and hit OK. And then I will load up the SolidWorks screen, and you'll see that it goes and it draws the cross sections over, and you see it creates the loft and succeeds. It sends all of this stuff over. See, I'm going to go ahead and hide those sketches. And for example, this lofted surface, I have a lofted surface that came from this 3D sketch. So we send over that 3D sketch. And you see you can hit edit. So you could edit that and recreate that if you needed to inside of SolidWorks. So we're sending the geometry over to CAD. Now, SolidWorks isn't the only place that we send to. You'll see that we have Creo, Inventor, NX, AutoCAD, Solid Edge. We can send geometry over to those locations. So you see how turbine blades are extremely complicated geometry, as we've talked about many times on this webinar. So you can see how you would model this entire thing and transfer the geometry over to your CAD environment or CAM environment and then work with it from there. So now let's just continue on. I'm just going to jump back over to my PowerPoint. And so what's next? Let's say that we went ahead and we created all of that geometry to recreate that turbine blade. And now we want to manufacture that turbine blade. Well, it just so happens that this same technology that you use to reverse engineer the part can also be used to inspect those parts as well, right? So that same scanner that you use to capture the 3D scan and create these polygon meshes to then create a CAD model, right? Like we just did, we showed that entire workflow and how it works. You can also take that same 3D scanner, 3D scan the part. You have the 3D scan, you have the CAD model because you modeled it, and then you can compare them together and create a measurement report on those as well. So you can leverage that same 3D scanner to not only reverse engineer, but also inspect off of that same data. So the same benefits of the 3D scanning, they can capture very complex geometry, it's mobile, all those same things function as an archive, apply to the inspection world as well, non-contact. But you also have benefits of measurement inside of software as well, right? So our Control X software is another software in our suite of 3D scanning based softwares. It's got a simple, modern interface. It has automatic feature recognition, and you'll see this here in a second. I'll do a short demonstration of how it works. It has really fast CAD comparison tools where you're comparing that scan data back to CAD. We also have the industry-specific things for the blade world, the RPS nest alignments, airfoil blade section analysis, which I'll show live, 2D twist analysis, easy 3D dimensioning, and then again, scans always kind of function as an archive. You can interrogate those 3D scans even more later. As long as you save those files, you can come back to them. So if I load up my Control X software, what you're looking at right now is I went ahead and I pulled in the CAD model for that blade and then the scan data. Now, I went ahead and set up our 6-point nest because that just takes a minute to do. And I set it up in a very generic way. This isn't necessarily following anyone's standards as to how to set up the 6-point nest, but you'll see that I went ahead and I already aligned that together. But what I wanted to do is show you how that we were able to do that, right? So one of the things that you need to do is 3D scans come in. They're out in the middle of nowhere in reference to the coordinate system of CAD, right? You need to align those two together. So to start out, what I did is I went ahead and did an initial alignment, which best fits these two different objects together. And then once I do that, we have a bunch of tools that will allow me to create reference geometry to then align these together using the RPS alignment. So one of the pieces of functionality that I utilize to create this RPS alignment is this concept of simulated CMM points. So I'm going to create one just to show you how this works. Now, we created these for a variety of different reasons, but one of them just so happens to work very well for turbine blades is when we made this scan-based inspection software, sometimes when you have, for example, if I need to measure this plane here, sometimes that measurement between that plane and this plane might be slightly different because, you know, if you measured that on a CMM many years ago, you're only maybe measuring 5 or 6 points to describe that plane. But now that we have 3D scan data, there may be a few thousand points describing that plane, right? So we created this idea of here where you can virtually probe the surface of the part. So you see here, we can create these virtual probe locations. And then I can select these virtual probe locations, and then I can create geometry out of those. So if I just come over here and I create that first one, and then we create the second one and third one, there. So we created 4, and then we'll go ahead and get out of this. So I created these 4 different probe locations. Now I can actually grab those 4 locations and create a plane out of those, right? So what this would do now is it's going to mimic probing those 4 locations on there, and then it will more accurately represent how we've always modeled these in the past, right? Because if you always probe those in the past, you can now like virtually probe these on the scan data. So that's where these virtual probe locations come from, is that ability to use these simulated CMM points. Now they also happen to work well because you can create probe points, but you can also create not just probe contact, but rod contacts, right? So I can actually say I want to create a rod contact, and then I can change my orientation here. I can say this direction, that direction, and then I can apply these like so. And I can apply my probe contact to the different directions. And then this is why it takes a second to set up, because you have to cycle through, and you can key these in if you already know the direction. But in this instance, this is why it takes it a minute to set up, is you can say that I want to create these simulated CMM points, which are essentially mimicking the fixture that you would set this in, the 6-point nest, to the way these are measured, right, historically. So you can create these simulated CMM points. And again, I created these as rod contacts, all 4 of these, and I created a point contact there. And then once I have them all created, I can come over to my RPS alignment, and I can select them, and I can say, I want to use this for alignment and this for alignment. We have all the RPS alignment functionality where I can say this one is only going to constrain in the X direction. This is only going to constrain in Y or Z directions. And you can apply your RPS alignment to the scan and the CAD model. So I already created that ahead of time. I'll go ahead and just turn that on. I finished out and I created this RPS alignment here. So you can see that now that RPS alignment exists. And now once it's created, it will remember all of the settings. And I don't need to create that every time. I can just drag in scan data again and again and measure it from there, right? So the RPS alignment is created, and now once we have our alignments created, I can go ahead and turn those off. We can start to create dimensions. So the first thing that people want to do is create a 3D comparison typically. So if we start off with coming in and creating a 3D compare, you can type in your values. If I want to override these dimensions, right, and rescale the color plot, I can do that. I can come in and I can create comparison points on the surface of the part. So I can measure specific locations on this object and say, hey, this is what the deviation is in these specific areas. Right. So these are all typical things that you might want to do with a 3D scan once you have that in 3D space. And then I can actually capture the screenshots here of the different individual measurements that I create. And I can even come in and reassign my viewpoints there. And from here, you can create those comparison points. You can create 3D dimensions. I'll just show a couple of those real fast. You can come in and say, I want to measure from here to here, and I can select and create dimensions on those surfaces, and I can type in my tolerances. And you see that we just measured the angle. So everything I measure on the CAD model, it's going to measure over on the scan data as well. So you can see I created that, and if I needed to measure the thickness from here to there, type in my tolerance. And you see that we created that dimension there. So I could go around and create all of those dimensions and then capture these screenshots like we talked about before. I can assign my views. But what's really interesting is you have the ability to cut 2D cross sections as well. So if I come over here, we'll just hide some of the geometry here, and I can actually cut 2D cross sections through the part the same way that I did dimensioning in 3D. So if I want to come in here and cut a 2D cross section, and you can see that the dotted line is the scan data and the dark line is the CAD information, and I can create dimensions the same exact way here. And if I needed to measure the center to center from here to there, creating those dimensions. And then I can even create an alignment as well. I can say, I only want to measure that in the X direction. So you're measuring from the center to center. And it's all the time pulling that same exact information from the scan data as well, right? So I'm measuring it off of the CAD, but it's creating the dimension off of both of them at the same time. We'll just say X again. Okay. So those are some of my 2D dimensions. If I want to go ahead and turn those off. Now, the final thing that I wanted to show here is the ability to also create airfoil dimensions. So if I want to, I can say I want to cut a cross section in the Z direction. Just set it for Z again, and then drag this up. I can cut a cross section through the airfoil, and I can set tolerances and do comparison there. But where I think this really shines is the ability to also dimension things that people typically want to know with the blade industry. So you can actually extract these different dimensions that are very specific to the turbine blade industry manually. See, so I can actually get the max chord length, the axial chord, max chord, chord length, leading edge radius. So you see here that we have very specific dimensions that we pull specifically for the airfoil itself, right? So you can kind of just dimension everything and cut your cross sections. And these are things that are very specific to this industry. And of course, all your dimensions are down in the table as well. We also create those same exact dimensions and analyze twist as well. So if I come over here and let's just type in that 43 again and hit next, We'll also calculate the XY twist. So we cut the section through, we best fit and calculate the twist analysis, because that is a critical dimension that people are always asking for. So you can see here that if I click on that we created that 2D twist dimension, and we have that down here in our dimensions table, right? So you can also calculate the 2D airfoil and twist, and then from there you can create a report. You can tell it, you can eliminate stuff that you don't want to report on, right? If you want to measure it but not report on it, you can throw things out. And then now I can come over here and I can say, let's export a report and save that as a PDF, PowerPoint, Excel. I can save it out as text files if I want to, XML files, all different kinds of information I can output that as. And then where this really comes into play is the ability to automate this entire workflow. So with this workflow, I can calculate and recalculate based on what I've already developed. So here's the report template. I can hit save PDF and we can write that out. Now, where the power of this software comes in is we've created this template here. So if I come over and I delete the scan data out of the file and then recalculate, you'll see that I'll have no dimensions. Everything will have a little exclamation point there, and there are no dimensions right on screen. But if I come over here and I pull in a scan again, you'll see it's not aligned. So if I just hit regenerate, this is kind of like a semi-automatic automation here, where I can tell it to automatically measure the same things on this piece of scan data, right? So that's one level of automation. Another level of automation is being able to come over and run a batch process. So with batch process, I could just point this to 30 scan files, 40 scan files, whatever it is, and then tell it to run and export reports on these. So it'll go grab each one of them individually, measure them, create reports, and output them to wherever I want. And then the final example of automation is we also have the ability to set this up as a server option, where our software will look and watch a folder, and as soon as a scan hits that folder, it'll analyze what the part number for that scan is, match it up with a template file. So you could have a bunch of different blade part numbers in there, and then it will grab the proper template file, measure and output on demand. So as the scans come in from a scanner, there is an automation server that will measure all of this on the fly. So that's the third level of automation. So now we have a few minutes where we could answer a few questions. If anybody has any questions, we'll go ahead and give people a moment if they have anything that they wanted to ask. But while I'm waiting, we can show this. If you need more information about our software, go to Oqton.com. You can download Control X or Design X at gettingstarted.geomagic.com. That's kind of our support portal. That's where our software is, and you can request trials there. And then we will have a video recording for this webinar available to everybody. So it doesn't look like we have any questions. So I just wanted to thank everyone for their time. Hopefully this was informative for everyone. And thank you everyone for attending this webinar on blade production and inspection from scan data. And again, we will follow up with a recording of this webinar for you if you need it. Thanks a lot.